Welcome, I'm Corey Kell, creator of FlatEarthIntel.com, and this weekly presentation we're going to talk about the three Norths: understanding direction and mapping. And when we mention the three Norths, I call them the three wise men. Why? Because they will show and take you places like no other on this earth. Let's talk a little bit about the three Norths. The first North we have is what we call the true North. They say Santa lives here. It's the real deal North. Look up for it on the map. On the globe, it's up towards the very top, and we'll show you an image of that, what I'm talking about. The next map is probably the most difficult North, is what's called Grid North. This is map reference Grid Sheet North. It's how it was drawn up, squares and all. It's basically a grid system. Magnetic North, the last one, which is actually what we call navigational North. It's follow the compass needle heading, it's drawn northward. So those are your three Norths: true, grid, and magnetic North. The differences in them is what we call the GM angle. And at the bottom of the diagram here, you'll see the difference. There's a difference in the actual location of each of these Norths, or if you were to look at measuring an azimuth to them, there's an actual difference. And this is what's called the GM angle. Typically you can find this on the bottom of a map sheet. Not all maps will have this on them, so you need to understand that. And this is what we call the difference between the Norths is called the GM angle, or the geometric angle. The first North that we talked about, the true North, is determined not by compass but by imaginary line of Earth's axis. And up here, this is for the globe now. This is true North for the globe, or the globe model. This is what they call true North, and the variation from the magnetic, what they call the magnetic North Pole on the globe model. And that's why I said look up for it on the map. You can see the difference there between the difference between magnetic and true North Pole. So again, that's what they're calling true North, and this is for the globe model. The next North is what we call Grid North. This is basically a grid system that was designed basically by the military. It's a grid reference system, and it's overlaid over the surface of the Earth, or what the surface as it's drawn to scale or imagery. And this grid system was developed or designed to help navigate and take you to these locations a little bit easier, where they want you to go and where they don't want you to go. The grid system can be used, and GPS kind of aligns with this. As you can see, this map sheet, this is the bottom of a map sheet, kind of shows you some information on this military map, but those grid squares, it's made up of all these little grid squares, and each grid square is 1,000 meters by 1,000 meters, and this is a military map system. Now there's also, we have latitude and longitude as well, so a little bit different scale than the military map system. Magnetic North, the last North, this is navigational or compass North. This is actually what you physically walk, drive, fly, or sail on Earth's surface. And so this is the difference in the Norths. And again, this is magnetic North, or what you're actually navigating, and when you physically navigate on the surface of the Earth. So this is magnetic North. So these are the three Norths. We've identified them. Let's identify the four cardinal directions. In this slide, we have north to 0 at 0 or 360 degrees. And then east, which is 90 degrees, south, which is the opposite of north, which is 180 degrees, and then west, which is 270 degrees. And again, this is navigational, or the four cardinal directions north. Very simple, nothing really hard. But when you hear the term cardinal directions, this is what we're talking about. Field expedient method of determining direction. In other words, we know our cardinal directions, but we're out in some place and we need to determine what the direction is. We don't understand where our direction is. We can use the sun and a stick. And this is sticks and shadows. I call it sticks and shadows the right way, not the Aristophanes way. And the military uses this, and I basically put a stick in the ground. As we know that the sun travels from east to west. We put that stick in the ground, and of course it casts that first shadow line, which would be rock position, or mark it by a stone position 1 there, as you can see on the top right. Wait 10 minutes, and then that stone, place another stone at that stick line shadow, which will be which will be as the sun travels, it will cast a shadow in the opposite direction. So then you'll have your east-west line, as we can see there. Like I said, it casts that shadow in the opposite direction, stone 1 from stone 2. Then all we're going to do is we're going to draw a line between stone 1 and 2. That's our east-west line. And then all we're going to do is draw a line diagonal. Remember we mentioned our cardinal directions. North is always to the east, or north is always to the right of east. So once we determine that by that field expedient method, then we can determine where we're at, or what direction we're at. So this is just a field expedient method, how the military does it. And again, this is sticks and shadows the right way. Navigation on a spear and on a flat earth. Really the same, but both models are laid out differently. The globe model, of course, we have the north up on the very top of the globe, south on the very bottom of the globe, and then east and west, left and right, or right and left. On the and you can navigate going around the globe, going east or west. The flat earth model being much different because the magnetic center is in the north of the flat earth model. So you can go east or west all the way around, left or right. You can get all directions on the flat earth model as you do on the globe model, but any direction outside of it is south. Meaning the magnetic north is in that center, and then a direction south is directly outside that. And if you were to use dead reckoning, eventually you would go south, eventually going left or right or top and bottom. Again, the north being in the center, being the magnetic center. So that compass will draw you in a circle just as it would on the globe model, going east or west, depending on your direction or your compass bearing. Very simple, but again, we need to know our cardinal directions, and we need to know how our navigation. Both models have all directions exist. Very simple. Gleason's flat earth map, again, this is how it's kind of laid out. Again, very simplistic. The center being the magnetic center, and then the latitude to longitude grid system. There's a scale on the Gleason's flat earth map which goes by using timing. Again, very simplistic but very accurate latitude and longitude for this grid scale system on this map. And again, magnetic north being the center, or the true north being the center of this map. So the main difference between these maps, between the flat earth map and the globe model map. We need to understand what the difference really means, and when I talk about that, we can take a sun plot. This is the flat earth model map. Sun position, we measured from sun position 1 here during OR2, or Operation Resolute Time, is a measured directional azimuth to the sun on a digital globe map at 91 degrees. So what we did is what it looks like on the globe map, the 91 degrees would be here on the globe map. For the Gleason's flat earth map, the measured directional azimuth to the sun on the FE map is at 88 degrees, so this is where it would be 88 degrees. Okay, so that's the difference. The difference being it's approximately 15 degrees. This is 15 degrees between 1 and 2. And the declination for Kabul is 3.36 easterly. Again, quite a difference from the flat earth map to the globe map. Now this is the difference on a flat earth map. Now we're going to show you the difference on a globe map. This is a globe digital map. Again, much different. The sun on a digital globe map, sun position 1, right here. So this would be on a globe, how it's plotted out. And again, from Kabul, Afghanistan, going out. This is about 1,100 miles. And roughly on here it's about 15 to 18 degrees, but I think it's closer to 15 degrees. Again, they use declination on the globe. Again, quite a stark difference from position 2, the sun on the flat earth map, okay, where the sun is located on the flat earth map. Again, a lot of difference. This is about 1,100 miles or 15 degrees. So you need to know what that looks like on both maps, the difference. And this is how we can tell how the flat earth map was altered from the globe model was altered from the flat earth model map. A lot of difference, about 1,100 miles or 15 degrees. That's how we can figure it out. The globe map and why GM angle is required. From what you're actually looking at, or what you're actually physically on, is a lot smaller than what the globe depicts. In other words, the original map size is smaller than what the expanded globe model version is. And then we're going to need GM angle to account for that. So, and we do that. So if you're originally here where this X is shown right here, we can use the expanded, on the globe map it's actually expanded out, you actually shift, and that shift is called the GM angle. Now, can we hide stuff using the GM angle, or can we hide stuff using declination? Yeah, it's kind of like GPS. We can GPS can take you where it wants and where it doesn't want to take you. Same thing here. Very cleverly, but you need to understand that difference in maps and how it works. And again, when you're talking about the globe, you're talking about a grid system. And military grid reference system was fitted on the globe. So remember when I talked about earlier, these grid squares are 1,000 meters by 1,000 meters square. And basically, you have these. There's a 100,000 meter grid square identifier, which is for this example here is Whiskey Delta or WD. So it's notated right here. And then read military maps right and then up. So the first one we're going to know, this star location right here is between 55 and 56. So it's 55. Halfway through is 500. So 5,500. And then the next grid coordinates would be 02500. Going up, it's halfway between 02 and 03, so it's 02500. So that's how we get our grid coordinates on a military map. Very simple, but again, very definite. And again, it'll keep you, it'll put you in places where it wants you, and it'll keep you out of places where it doesn't want you. So very cleverly, we need to understand that. And that's, again, this is the military grid reference maps, and this same thing with GPS. Again, most maps will show you a scale. This one's red light readable. This is a military map. And again, these are these grid squares, what I was talking about. And they have identifying numbers on them. Very simple. And on the bottom of the map, you have the legend or the scale. Shows you the GM angle at the very bottom. And we'll give you a blow up on the GM angle. We're going to give you an example how to do a conversion on GM angle. Very simple. On the map itself, it'll actually tell you to add or subtract the GM angle, whatever it is. In this example, we're going to go from a magnetic azimuth of 270 degrees to a grid azimuth of 261. Remember, magnetic azimuth, we're actually navigating. Now we need to plot it on a map. On the map, that's the grid. So we're going navigation, what we're actually physically walking on. We're measuring an azimuth. We need to plot that on a map, and then we need to convert that to put it accurately on a map. So for this example, we have to subtract 8.5 degrees. That's the GM angle, the difference between magnetic and grid. So our 270 degrees heading, we subtract 8.5 degrees, which would be 261 grid on the map. So on the map, we would plot 261.5 degrees on the map. That would give us the same heading as we're navigating. So again, that's how you do the conversion. Okay, that's going from navigation or grid compass north to a grid north. In the next example, we're going to do just the opposite. Now we're going from a grid, we're going from a map sheet, we measured 98 degrees. Now we need to convert it to a compass or a heading, what we're actually walking on. So in this conversion table, it says to add the GM angle. So now we're going to add the 8.5 degrees. So we have 98 degrees plus 8.5 is 106 degrees. Is going to be our magnetic heading. And that's the conversion we need to walk. We need to walk 106.5 degrees from the map. Okay, and that's GM angle. That's how we do the conversion, and that's the difference, and that's the GM angle. Again, nothing really difficult. We just need to understand the difference in Norse and what model we're talking about. I'm Corey Kell, creator of Flat Earth Intel. This concludes this week's presentation on the 3 Norse. Thanks for watching.